Welcome to the lesson on section 6.5, average value of a function. In this lesson, you'll learn how to use integrals to calculate the average value of a function, and we'll look at how the mean value theorem applies to integrals. In example 1, the normal mean air temperature in Fairbanks, Alaska can be found by the function f of x equals 37 sine 2 pi over 365 times x minus 101 plus 25, where x represents the number of days since January 1st. What is the average temperature over the first 100 days of the year? Let's look at a derivation of a formula. Consider the function f of x shown in the graph. We'll develop a formula for the average value of f over the closed interval from x equals a to x equals b. Suppose we split the interval from a to b into n partitions. Then the average value of function f would be found by adding n values of f together and dividing by the number of items, which is n. The width of each of these intervals would be b minus a divided by n. Rearranging this formula, n equals b minus a over delta x. Substituting for n in our average value equation, we get this. Treating the division of this fraction as multiplying by its reciprocal, we get 1 over b minus a times the sum of each function value times delta x. The average value of the function would be the limit of this expression as n, the number of partitions of the interval, approaches infinity, or 1 over b minus a times the integral from a to b of f of x dx. Returning to our example, the first 100 days would represent an interval from 0 to 100. Using our formula, we get 1 over 100 times the integral from 0 to 100 of f of x dx, and we would integrate from there. The second example asks us to find values for the constants a and b so that the function f of x equals x squared plus ax plus b has an average value of 2 on the interval from 0 to 1 and an average value of 1 on the interval from 0 to 2. First, I'll use the average value formula to set up two equations. One showing that the average value from 0 to 1 is equal to 2, and another showing that the average value from 0 to 2 is equal to 1. From here, you would complete the integration and solve the resulting system of equations for a and b. If you'd like to finish this problem as an exercise, you should end up with a is equal to -4 and b equal to 11/3. One consequence of the average value formula is the mean value theorem for integrals. The theorem says that if a function f is continuous on the closed interval from a to b, then there exists a value c in this interval such that f of c is equal to the average value of f on this interval. Multiplying the b minus a from the average value formula to the other side results in the equation f of c times b minus a equals the integral from a to b of f of x dx. Thinking about this geometrically, the theorem really says that we can pick a value c between a and b such that the area of the rectangle with height f of c and with b minus a, which is shown in red in the diagram above, is equal to the area under the curve from a to b, which is shown in green. You might recall that we've already been finding average velocity another way. Let's look at how the method we used at the beginning of the year compares to our new average value formula. Using the formula, the average velocity from time A to time B is equal to 1 over b minus a times the integral from a to b of the velocity. By the fundamental theorem of calculus, or the net change theorem, this integral equals any antiderivative of velocity at b minus any antiderivative of velocity at a, or the position of the particle at b minus the position of the particle at a. At the beginning of the year, we considered instantaneous velocity to be the slope of the tangent line to the position graph, while average velocity was the slope of the secant line to the position graph. That's what this expression represents. Notice it's a change in y over a change in x from the position graph. So our new average value formula should result in the same average velocity we've been finding since the beginning of the year. This concludes our lesson on section 6.5, average value of a function.